Algebra 2. How you doing? So some of you requested a practice lesson on factoring. So I'm going to just go through different types of examples of factoring. And then I'll give you a practice worksheet so that you can kind of try some on your own. Because this is definitely going to be something we're going to use the rest of the year. So if you're not feeling 100% comfortable with it, make sure that you practice it. And if you're still struggling with it, then come to office hours because it's super important that you got this. All right, so different methods of factoring. You got all sorts of different ways to factor. All right, I just want you to have this just in case you wanted it, but the formal definition of what factoring actually means is basically that you get everything in a form that no part of the expression can be made simpler by pulling out a common factor. So like x cubed minus 2x plus 3 is not in completely factored form because this part you could pull out an x. And so basically, when you're factored, you want everything broken up into factors, which are things multiplied by each other. Okay. Okay. So here goes. First one. Factor p squared minus 5p minus 14. So this is your basic factoring. Your first term, your a term, is 1, so you don't have to worry about that, right? So basically all you have to look at is what numbers multiply to negative 14 and add to equal negative 5. And so for negative 14 you have 1 and 14, and then you have 2 and 7, and then you could have plus or minus because it's negative 14, so you need negative 1, positive 14, or positive 1, negative 14, right? So basically we need to pick which combination of those, pluses and minuses and 7s and 2s or 1s and 14s, that would get us p, so that when we add them together we get negative 5, okay? So hopefully you figured that out already. That's negative 7 and positive 2. Those multiply to negative 14, add to negative 5. So you end up with p minus 7 times p plus 2. So that's your most basic type. The second problem, the one below it, is very, very similar. So if you want to practice that first, pause it, try it on your own, and then check the answer. Pause. Okay, what multiplies to 63 adds to negative 16? Well, 9 times 7 is 63, and if you add 9 plus 7 you get 16, but we need a negative 16, so it's going to be a negative 9 times a negative 7, because a negative times a negative is a positive, but adding a negative plus a negative, that's a negative. Okay, so that's going to work. So then you just end up with x minus 9 times x minus 7. Alright, number 3, which I'm deciding to label this as 3, has 7k squared plus 9k. And this one's a little different because it doesn't have 3 terms. Okay, it just has the 7k squared and the 9k. So probably the best way to look at this problem is to see if there are any terms that you can pull out. So since you have 7k squared plus 9k, right, both terms have a k. So you can actually pull that out. You can't divide it out because it's not an equation. You can't just like get rid of it, but you can pull it out and you end up with a 7k plus 9 left over. Okay, and you can check and make sure that is equal to what we started with, because if you distribute that k back in, you get 7k squared plus 9k. Okay, so yeah. Okay, next problem, 4, x squared minus 9. So this is a difference of two perfect squares. Okay, so this is a special case because you have something squared, right? That's x. X squared is x times x, right? So that's a perfect square. And then 9 is also a perfect square. That is 3 times 3. Okay, so I can actually rewrite this as x squared minus 3 squared. And so now we have the difference of two perfect squares. All right, and the way you factor the difference of two perfect squares, I mean, really all you're trying to figure out is what numbers multiply to get negative 9, add to get 0, and factor it like the normal way. But anytime you have a difference of two perfect squares, it factors really nicely. So anytime. So I'm going to do this in pink just so that you know this is like notes kind of thing. But if you have something squared minus something else squared, as long as it's like in that form, then you can factor that to be a minus b, or that something minus something else, times that something plus something else. And that always ends up being the correct thing, because when you multiply this out, you get a squared, and then you get positive ab, then you get negative ab, so those cancel, and then you end up with the minus b squared. Okay, so it will always work out if you have a difference of two perfect squares. So in this case, we have x squared minus 3 squared, and so our a is x, and our b is 3. So this ends up factoring as x minus 3 times x plus 3, right? It's the same thing as we had up here in our little note section, okay? You could try the next problem. It's also a difference of two perfect squares. So try it. Go ahead. All right, so number 5. It is a difference of two perfect squares, but you have to make it look like two perfect squares first, okay? The problem is here you don't have something squared and then something else squared, okay? So you have to make it look like that first before you can factor it. So this 4 is the same thing as 2 squared, and that's times x squared. So that's kind of the same thing as, not kind of, exactly the same thing as 2x squared, because remember the square and exponent can distribute over multiplication, just not addition or subtraction. Okay, and then 25 is 5 squared, so I actually end up with 2x squared minus 5 squared, so then that factors to be the first thing minus the second thing times the first thing plus the second thing. So I've got 2x minus 5 times 2x plus 5. Easy breezy. We like perfect squares. Alright, the last two are problems where the number out front, the a value, is not 1, and you can't pull it out. So if you notice, like I can't pull out a 2 from all of these terms, because if I do that, then I have 2b squared plus 17 over 2 and b, and 21 over 2b, or 21 over 2. So that's kind of not an ideal situation. We don't like factoring with fractions. So that's not how you want to solve that problem. In a case where you can pull the 2 out, then do that first and just factor it like we did 1 and 2. Okay? But anyways, so this case, right, I'll show you the steps again to go through a problem like this. Now, one option is just a guess and check, which I think is what you guys have learned in the past, which is fine. Nothing wrong with that. And some people, I think, have learned like this, the x thing or lattice thing. So you can do it those other ways. I have no problem with it. I just prefer this method because it works every time. I like it. But you need to make sure that you do the steps right, because if you don't do the steps right or you forget something, then it doesn't work out. Luckily, you can always check your work at the end and make sure that it factors or foils back to the thing that you started with. So anyways, step 1, 2 that beginning 2, the a value, goes and visits the c value, the last number, okay, and they multiply together. So then you have b squared plus 17b plus 21 times 2, which is 42. Okay, so then we want to factor that. So we want to find the values of 42, the factors of 42 that add to 17. After a little thinking, you could probably figure out that's 14 times 3. So this factors to be plus 14 and b plus 3. Okay, so that's your next step, is just factor. Okay, so you factor, then you bring the a back into both terms, okay, both factors. And in this case, a is 2. And then because you brought 2 back, you're only allowed to bring 1 back. You have to divide a 2 out of the factors. So easiest one to divide out of is this first one. Divide this one by 2, you end up with b plus 7 times 2b plus 3. And you can FOIL that out and make sure that that works. You've got 2b squared plus 3b plus 14b, so that's 17b. Good there. And then the last term is 21. Yay! And then it's factored. And that's your answer. All right, this last problem is going to be a combination of different strategies. So if you look at it initially, like 21 or 28 n to the 4th, like, we haven't done n to the 4th. It's okay, because this one has an n to the 4th, this one has n to the 3rd, and this one has n squared. So that means all 3 of them, you can pull out an n squared. In addition, every single one of those numbers, 28, 16, and 80, are all divisible by 4. So you can actually pull out, before you do anything else, any actual like factoring, even though this actually is factoring, you're factoring out a 4n squared, you want to pull out the 4n squared, because then it makes what you're factoring a lot simpler. Okay, so when you pull out a 4n squared, the 28n to the 4th, you're left with 7n squared. The 16n cubed, you're left with 4n. And the minus 80n squared, you're left with minus 20. And so now all you have to do is factor this inside part. Don't forget about your 4n squared. That's still there. It doesn't disappear. But it's just out there. Chilling out there, and then you factor the rest of this. Okay? And then I'm going to do that the same way that I did the previous problem. Take the 7, go and visit the 20, you've got n squared plus 4n minus 140. And then you want to figure out what multiplies to negative 140, adds to positive 4. Well, I think 10 and 14, sorry, 10 and 14 multiply to 140, right? And we want it to be positive, so we've got negative 10 and a positive 14. So this factors to n minus 10 times n plus 14. You put the 7 back in, then you have to divide 7 out. Makes the most sense to divide it out of the second one. Okay, so then you're left with 7n minus 10 times n plus 2. And don't forget, you have that 4n squared on the outside. Okay, and that is your entirely factored function. Hey! And then you can get your zeros too, right? If it were a function, right? You set this equal to 0, you set this equal to 0, and you set this equal to 0. In this case, you have 4 zeros. So, good job. Go practice. Make sure you can do this. Okay, bye!